Hi everyone. So in this video, I'm going to go over some of the questions from the final exam review. I decided to split it up basically halfway among the questions that people requested to go over. So in this video, we'll be going over questions that kind of end around related rates. So not so much like the first half of the class, but just the first half of the questions that were requested basically. So yeah, let's get into it. So first question that was requested was number 1. So number 1 is giving us a function and we're asked to find some limits. So I'm just going to copy that function back down over here. So we have f of x is a piecewise function. It has 3 pieces to it. And I guess I should have made these brackets a little bigger. So the first piece we use if x is less than 0. The second piece we use if x is between 0 and 3, including 3. And then the last piece we use if x is bigger than 3. So I want to make it clear that you actually do not need to draw the graph in order to answer this question. I'm going to draw it just because I think it will help you understand actually how you could do this without drawing the graph. I think just by having a picture to refer to, maybe it will help you understand what you could do without even having the graph. Hopefully you'll see what I mean when we get there. Okay, so what does the first part of this graph look like? So square root of negative x. So that's going to look similar to the graph of square root of x, except for that it's going to be reflected horizontally, so reflected over the y-axis. So that's going to look something like this. Oops, let me do that a little better. So why does it look like this? Well, for example, if you plug in -1, you get square root of negative 1, which is positive 1. And the square root of positive 1 is 1. If you plug in -4, you get the square root of negative 4, which is positive 4. And so the square root of positive 4 is 2. So that's the first piece of the graph. And then there's something I should add here, which is that because this says less than, it doesn't say less than or equal to, we have an open circle on the graph. So this point is not included in that portion of the graph. Okay, so second part of the graph is 3 minus x. So what does that look like? Well, that is a line with a slope of -1 and a y-intercept of 3, right? It's like negative x plus 3. So that's going to look like this. And we're supposed to use that from 0, including 0 as an x value, up until 3, also including 3. And then the last part of the graph is x minus 3 squared. And so what does that look like? That's a parabola that has been shifted to the right by 3. So, and hasn't been shifted up and down at all. So the vertex is at 3, 0. And so that's going to start right where the purple one leaves off, and it's going to look something like this. So it's like half of a parabola, but it meets perfectly up with the purple one, right? Because they agree at that point. And so I don't need to make an open circle, even though it's greater than, because those 2 points overlap anyway. So really the only purpose of putting an open circle is to emphasize the fact that, that there is no point at that point with the open circle. Okay, so why did I draw this picture? Basically, I just wanted to show you kind of how you can go through each of these limits and think about them by kind of referring to the picture. So the first limit that we're asked to find is the limit as x approaches 0 from the right of f of x. So looking at the picture, we know that if you're approaching 0 from the right, that means we're basically looking at, as you get closer and closer to 0 as your x value, what is the y value approaching? And we can see that the graph is getting closer and closer to 3. So how could we have answered that without looking at the graph? Well, we could have plugged it in to this function. So how would I know without, if we didn't have the graph there, that you could plug it into this function? Well, you want to think about which of these 3 equations are you using for values that are just above 0, right? Because we're doing 0 from the right. So the first equation, square root of negative x, that one you use when x is less than 0. So which equation do you use when x is just above 0? Well, you use the second equation. And so without drawing the graph, you could have just gone in and said, okay, well, I can see that, when x is greater than or equal to 0, we use the second equation. And so you could have just plugged 0 into that, right? And you'd get 3 minus 0, which is 3. So it agrees with what we saw on the graph. And by the way, it doesn't matter the fact that we have the equal sign here. That really doesn't matter when you're doing this, because limits don't care about what the function is, what's happening at that particular value. It only cares what's happening close to that value. So if this had been instead just greater than and not greater than or equal to, we would still use this middle equation, because we're really just focused on what happens when x is just above 0. Okay, so next question is asking us the limit as x approaches 0 from the left of f of x. So again, let's start by looking at the graph, and then I'll explain how you could do it without using the graph. So looking at the graph, we would be saying, okay, well, as x is getting closer and closer to 0 on the left of 0, where is the function heading? And in this case, it's heading to a y value of 0. Right, if we look at the graph. And it does not matter that there's an open circle on the graph there, because we don't care what's happening at x is equal to 0. We only care what's happening as x gets close to 0 from the left. So similarly, because this is the function, the first function is the one that you use when x is less than 0, you could plug 0 into that equation. So if you took the square root of negative 0, that would give you 0. So rather than look at the graph, you could have just plugged 0 into the top equation. Again, you might look at that and say, whoa, wait, why can we plug this in? This says if x is less than 0, why are we plugging 0 into that? Well, it's because we're not worrying so much about what's happening at 0, we're just caring about what's happening close to 0. And so even though this function is not defined at x is equal to 0, because it's kind of heading towards that point, we can still plug 0 into it. It's kind of like telling us if the function was defined at 0, where would it be going, right? It's like if this function continued, where is the trend going? And so that's why we are allowed to plug in 0. Okay, so part C is asking us for the limit as x approaches 0 of f of x, so now without the left or the right. And so that's asking us basically to see, do the left and the right sides agree? And they do not. So we would say it does not exist. The limit does not exist because the left and right hand sides don't agree. So looking at the picture, we can see that because we have this gap in the graph, right? There's no kind of consensus about what's happening when x is close to 0. It really depends if you're to the right or to the left. Okay, so we're also asked to do the same thing for 3. So we're going to take the limit as x approaches 3 from the right, or I guess I flipped the order. So I said from the left first for some reason. Okay, so again, looking at the graph, if we're approaching an x value of 3 from the left, that means we're looking here, right? We're seeing what y value is the graph getting closer to as x gets closer to 3 on the left. And we can see that the graph is getting closer to 0. So how could we have done this without looking at the graph? We could have plugged it into this equation, right? Because if we're looking for what happens when x is just less than 3, so to the left of 3, we see that this is the inequality that matches that, right? So that tells us if we plug in 3 into this middle equation, we get 3 minus 3, which is 0. And so our answer is 0. So next question is the limit as x approaches 3 from the right. So looking at the graph, we're looking at now coming in from the right side and seeing what y value is the graph getting closer to, and it is also getting closer to 0 on the right. So using these equations, now we would be using this equation, because this is the equation that you're supposed to use when x is to the right of 3. And so again, even though this doesn't say greater than or equal to, that doesn't matter. We can still plug 3 into that because we're just trying to figure out where would the graph be heading. And in this case, if you plug in 3, you get 3 minus 3 squared, which is 0. And so it happens to agree with what happened in the middle equation. And that's why these match up, right? Because you get the same thing by plugging 3 into the middle and the second equation, that's why the graphs match up perfectly. And so because of that, we can say that the overall limit is equal to 0 because those two agree. So the last question was asking, where is f of x discontinuous? And so that means basically, what are the places where it, where there's a break in the graph of some sort? And so we can see that it is continuous at 3, right? That's like where, maybe just to step back for a second, where should we be looking? Like, what are the possible places it could be discontinuous? It would just be the places where the graph meets up. Because all of these functions themselves are continuous, they don't have any asymptotes or any funny business going on. Because the 3 functions here are continuous, the only thing we have to worry about is the places where they match up. So we just would need to look at 0 and at 3. So we can see that at 3, the pieces of the graph match up. So how could you have figured that out without looking at the actual graph? Well, basically because the left and right limit agree with each other, and because the function is defined at 3, right? If you plug in 3, you would also get 0. That's what tells us that it's continuous at 3. So what about at 0? Well, at 0, we see that the left and the right limit do not agree with each other, and so therefore it is not continuous. So it is not continuous at x is equal to 0. Okay, so let's look at the next question. So next question is number 2. So this also has to do with continuity. So this question is asking you to figure out, where is the graph of f of x is equal to 5 over x plus 2 plus minus 1 over e to the x, all divided by e to the x minus 1, discontinuous. So for figuring out whether functions are continuous or discontinuous, basically, if you have a piecewise function, so like the one up here, then you have to worry about, again, these places where the different pieces like match up, because those are places where, depending on the equations, there could be a mismatch, there could be gaps in the graph. For functions that are not piecewise functions, really all you have to worry about is figuring out, where is the function undefined? Any place that the function is undefined is going to be a place where it's not continuous. So basically, this is the same thing as saying undefined. So we basically just need to figure out, what could kind of make this function go wrong. So what could make this function go wrong? Well, basically, if any of the denominators in this function equals 0, then that will make it undefined. So we need to figure out which values of x make the denominators, and I'm using a plural here because this is a function with multiple denominators going on. We need to figure out which values would make that happen. So we have 3 different denominators, right? We have this denominator, and this denominator. So what would make x plus 2 equal 0? That would be when x is equal to -2. And so basically, if you try to plug in -2, you'll see that this function is undefined at -2, and therefore it is not continuous at -2. So our second denominator, and maybe let me just color code this. So our second denominator was e to the x. So is e to the x ever equal to 0? No, right? There's no number that will ever make that 0. And so that basically tells us that, there's no solution, and that doesn't mean that there's anything wrong. That just means that that part of this function is not going to contribute any discontinuities. And then the third denominator we have is e to the x minus 1. So if we solve this one, we get e to the x is equal to 1. And that tells us, so what power would you need to raise e to get 1? You would need to raise it to the 0 power. And so that tells us x is equal to 0. So x is equal to -2 and x is equal to 0 are the two x values that make this function undefined, and therefore they're the x values that make this not continuous. All right, so next up we have a few limits. So this is going to be number 3. So we're going to start by doing h. So h is, and actually maybe before I even get into this, I want to just sort of like write down kind of a general process that you might think about for limits, or general kind of strategy for limits. So if you're evaluating a limit, what's the very first thing you want to try? You probably first want to try to plug in the number. See, if you're taking the limit as x approaches a of a function, try plugging in x is equal to a. If nothing goes wrong in your function, then you're good. And actually, maybe even before that, I should say one thing, which is that if your function is piecewise, so that's like the first example we did in this video, then you're going to want to find the left and right hand limits separately. So really it's only in piecewise functions that we're going to really be thinking about left and right hand limits. It's not really the only time it comes up, but for the sake of what we're doing in this class, that's probably the only time that you'll have to deal with that. So how do you find them separately? You use the different equations, right? The different equations that make up your piecewise function. So just like what we did in the first question. So second thing is if your function, and maybe let me take this 3 off here because this might look a little confusing now. So if your function is not piecewise, then basically that's kind of that's like the usual situation, right? So if the function is not piecewise. So the first thing you want to try is try just plugging in the number. So the number where you're trying to find the limit. If f of x is defined at that number, then great. That's your answer, right? If you can just plug in the number and get an answer, you're good. So second thing you might want to try is basically look at if you have an indeterminate form. So is your function, or sorry, let me maybe say it is, I'll say it this way, is the limit indeterminate of the form, so the ones that we talked about in this class were infinity over infinity, 0 over 0, or 0 times infinity. So if that's the case, you can use L'Hopital's rule. And in some cases, we saw that there's other methods you could use, like you could use some algebraic simplification, but generally speaking, L'Hopital's rule is a little bit easier. So if you can't use L'Hopital's rule, indeterminate of the forms mentioned above, then you can try algebraic simplification. So as I just mentioned, there's a lot of situations when you use algebraic simplification that you could also use L'Hopital's rule. But there's some exceptions. Like, for example, we had some examples where you had to make a common denominator. So that would be like number 3G on this review. That would be one where it's not an indeterminate of any of these forms, so you have to make a common denominator. And then lastly, if none of these things work, so if you can't simplify or use L'Hopital's rule, or use algebraic simplification. And if the function contains sine or cosine, then you can try the squeeze theorem. Okay, so let's, with all these kind of steps in mind, get into some actual examples. So number 3 on the review was just a bunch of limits. So h is the limit as x approaches 0 of x squared times cosine of 1 over x squared. So let's kind of run through the list of approaches here. So first thing you want to try is plugging in the number and seeing if your function is defined or undefined. So if we try to plug in 0, we get 0 over here, which is fine, but then we get cosine of 1 over 0. 1 over 0 is undefined. So it would not be correct to say here, oh, well, we have 0 times something, and so our answer is 0. The answer we'll see does turn out to be 0, but that's not a valid way to show that because this part is undefined when x is 0, it kind of scraps the whole thing. It tells us this whole thing is undefined at x is equal to 0, and so therefore we cannot just plug in 0 for x. It does not work. So the next thing we might think about is, can we use L'Hopital's rule? But again, if part of your function is just straight up undefined and doesn't have a limit of infinity, so the limit as x approaches 0 of this part is not equal to infinity, right? It's just, it doesn't exist. We can't even figure out what that limit really is. And so this is not a L'Hopital's problem because we don't have 0 times infinity, we don't have infinity over infinity, we don't have 0 over 0. So what are we left with? Well, our function does involve sine or cosine, so that tells us that this is a squeeze theorem problem. So how do we use the squeeze theorem? So basically, you want to figure out what are the two functions that this function is in between, and then you're going to find the limit of those functions. So in general, the way you want to start is take your trig portion, so here cosine of 1 over x squared, and cosine of 1 over x squared, we know that that has to be between -1 and 1. And I guess there's one thing that I haven't been saying that maybe I should have said from the get-go. This inequality is basically only true for all x that are not equal to 0, right? As soon as x is equal to 0, then this whole thing is undefined, so this statement doesn't make sense. But because with limits, you're not worried about what happens when x equals 0, right? You're just worried about what happens when x is close to 0. And so that's why that's why we actually have to even use the squeeze theorem, is because it's undefined. And so we can write down this statement and say, okay, that's for all x not equal to 0. And then we're trying to find the limit of x squared times cosine of 1 over x squared. And so that tells us that we want to take this inequality and just multiply everything by x squared. And again, that's for all x not equal to 0. So from here, well, now we know that we have two functions that x squared times cosine of 1 over x squared is between, right? If you were to graph this, you would see that, x squared and negative x squared, one of them is a right side up parabola, one is upside down, and then x squared times cosine of 1 over x squared is like a squiggle that goes between them. So it's right between the two of them. So if we can show that the limit as x approaches 0 of negative x squared is the same as the limit as x approaches 0 of positive x squared, then we can conclude that the function that is in between them must have the same limit. So the limit as x approaches 0 of negative x squared, that one we actually can plug in 0, right? Because there's nothing that's undefined. And for x squared, we can also plug in 0. And so from here, we can conclude that the limit as x approaches 0 of x squared times cosine of 1 over x squared is also equal to 0. So I mentioned this a few times, but basically when you're using the squeeze theorem, I want to see all of these steps. I need to see you kind of declaring, what are the functions that your function is in between. I need to see you write down the limit of each of those functions and then use that to conclude that you have the same limit. So on previous tests, people got points off on questions like this because you never kind of expressed the limits. You kind of wrote down this stuff and then we're just like, oh, well, that means that, 0 is less than or equal to this stuff is less than or equal to 0. And that just doesn't really make sense because you're not plugging 0 in, you're taking limits. And it's a subtle difference, but it's one that I do want to kind of pay attention to when I'm grading. Okay, so the next question we have is the limit as x approaches 0 of e to the x minus 1 divided by tangent of x. So we can try to plug in 0 and see what we would get. So if we were to try to plug in 0, in the numerator, we would get e to the 0, which is 1. So 1 minus 1, which is 0, over tangent of 0, which is 0. And so this is an indeterminate of the type 0 over 0. And so that tells us that we can use L'Hopital's rule. So what does L'Hopital's rule say? It basically just says you can take the derivative of each part of your limit. So this first limit we started with is the same as the limit of taking the derivative of the numerator and the derivative of the denominator. So let's see what that gives us. So the derivative of e to the x minus 1 is just e to the x. And the derivative of tangent of x is secant squared of x. So now let's try to plug in 0 again, and we'll basically see, either we'll get a number, which means, okay, great, then we have our answer, or if we get 0 over 0 again, then that tells us we have to use L'Hopital's rule again. So what do we get if we plug in 0 for e to the x? We get e to the 0, which is 1. And then what about secant squared of 0? Well, secant, let me write this down here. So secant squared of 0 is the same thing as 1 over cosine squared of 0. And what is cosine of 0? Cosine of 0 is 1, and so that gives us 1 over 1 squared, which is the same thing as just 1. And so we get 1 over 1, and so the answer for this limit is 1. Okay, so next up we have k. So k is the limit as x approaches infinity of square root of x over ln of x. So let's start by, so when you have a limit at infinity, there's no chance to even plug in. Like, I really don't want you to think of plugging infinity in because infinity is not a number. So you can't just plug infinity in, but what you can do is take the limit of the numerator and the denominator separately. So the limit as x approaches infinity of square root of x is infinity, right? The bigger the number you take square root of, the bigger your result. So the numerator goes to infinity. And then what about the limit as x approaches infinity of ln of x? That is also infinity. So those are ones that you probably want to kind of just know off the top of your head. And if you go back to the video where I first introduced L'Hopital's rule, I gave you some examples of like e to the x, ln of x, some other just types of derivatives that, or sorry, limits that you just should kind of be aware of without having to do any work to find them. So that tells us that this is type infinity over infinity, and so we can use L'Hopital's rule. So the limit is going to be the same as if we take the limit as x approaches infinity of square root of x, the derivative of that, over the derivative of ln of x. So what is the derivative of square root of x? Well, we know that that is 1 over 2 root x. And then what is the derivative of ln of x? Well, that's 1 over x. And so before you go and evaluate or think about whether you have to use L'Hopital's rule again, you always want to see if you can simplify. So how can we try to simplify this? Well, we can rewrite this as 1 over 2 root x times x over 1. So that's going to be the limit as x approaches infinity of x over 2 root x. And you could use L'Hopital's rule here again, but you can actually simplify this even further. So x over the square root of x, well, that's just going to be square root of x, right? If you do like 9 divided by the square root of 9, you're left with 3, which is the square root of 9. So x divided by the square root of x is just going to give you square root of x. So we're going to have 1/2 times the square root of x. And you could also do that by subtracting exponents, right? You'd have 1 and 1/2, and if you do 1 minus 1/2, you get 1/2. So we're left with 1/2 times square root of x. And so now we can just actually evaluate this limit. So we know that the limit as x approaches infinity of square root of x is infinity, and that 1/2 isn't going to affect that, right? It's going to make the graph go towards infinity a little slower, but that doesn't really matter to the fact that the limit is still infinity. Okay, so next up we have some derivative questions. So let's see, I think this is number 5. And actually, let me just say one thing real quick before we get into that. So no one requested to go over questions from part 4, but I just want to quickly mention that make sure that you know how to still use the limit definition. So I guess I should have maybe even here said the limit definition. There will probably be at least one question or just one question on the final where I'll ask you to use the limit definition of the derivative. So on that question, just like on the first midterm, if you don't use the limit definition, you're not going to get points for that question because that's really what I'm testing. So make sure that you know how to do that. But yeah, we're going to look at a few questions from number 5. So I'll still keep going on this page, I guess. So number 5, I had a request for B. So B is asking you to find the derivative. So now we're just using derivative rules. So this one is the derivative of ln of x times ln of x. So there's 2 ways to do this. One thing you could do is you could use the chain rule and then use the product rule, right? Because we have our outer function would be ln of u, and our inner function would be x times ln of x, which is a product. But anytime you're doing ln of something, it's worth checking whether you can first simplify your answer, because that's just going to make, if you can use logarithm rules to simplify, that will just make the derivative part easier. So we can start by simplifying this. Basically, anytime you're taking a logarithm of a product, like we are here, you can split it into 2 pieces. So we can split this into ln of x plus ln of x, which I know is like a little confusing of a function. But we'll get there in a second for taking the derivative. So what is the derivative of the first part going to be? Well, that's going to be 1 over x. And then for this part, this is still kind of a tricky derivative because we have to use the chain rule, but at least we don't need to use the chain and product rules together. I think that just always makes things a little trickier. And especially, I like to see your answers simplified, and I think it's usually easier to simplify before taking the derivative than after. So for this function, I just want to kind of write this one out because I think because it's ln of ln, there's something about that that makes it a little bit more confusing. So in this case, the outer function is ln of u. And the inner function is ln of x. So what is that going to look like for taking the derivative? Well, the first part of the derivative is always the outside derivative, right? So the outside part of the derivative is 1 over u. And what is u in this case? U is ln of x. So it's 1 over ln of x. Just the same way that, like, let's say this was ln of sine of x or something, you would do 1 over sine of x. Or if it was ln of 5x, you would say 1 over 5x. Or if it was ln of secant of x, you would say 1 over secant of x. Whatever function's in there, you do 1 over that. Then we have to multiply by the inside derivative, and so that would be the derivative of ln of x, and that derivative is just going to be 1 over x. And so altogether, our answer comes out to be 1 over x plus 1 over x times ln of x. All right, so next up, let's look at another derivative. So we're going to look at d. So 5d is y is equal to sine of x plus 1 over tangent of x. So this is another one where there's multiple ways to do it, but where if you can simplify before taking the derivative, you're going to make your life a lot easier. So if you didn't simplify it, you would have to use the quotient rule, right? And you know, that would be fine, but it would take a little bit more work to kind of get your answer into its simplest form. So how do we simplify this? Well, we can start by splitting it up. And by the way, like, what makes me say, like, why do I look at this and think, oh, let's simplify it? Well, basically the fact that we have multiple trig functions going on, you know, I kind of think like, well, maybe if I write sine of x over tangent of x, you know, there might be a way to simplify that. And then also, you know, 1 over tangent of x, we know that that is equal to cotangent of x. So I kind of can look ahead and say, you know, there's probably going to be some ways to break this down a little easier. So how can we simplify sine of x over tangent of x? Well, we can write it as sine of x divided by sine of x over cosine of x, right? Because tangent is the same as sine of x over cosine of x. And then you could kind of go either way here. I'm going to rewrite this as cotangent of x. You might not remember the derivative of cotangent of x. That's one of the ones that probably doesn't stick in your mind as well. So you could totally leave this as 1 over tangent and just use the chain rule. And it's a pretty easy chain rule because it's 1 over something. Okay, so how does this simplify? So sine of x over sine of x over cosine of x. Well, that's the same thing as sine of x times cosine of x over sine of x. So that cancels out and we're left with just cosine of x plus cotangent of x. So now we're ready to take the derivative. So the derivative of cosine of x is negative sine of x. And then the derivative of cotangent of x, like I said, you might not remember this one, but it is negative cosecant squared. Oops, cosecant squared of x. But like I said, if you use the quotient rule for that, for finding, if you did it instead as 1 over tangent, that would be pretty easy. You're totally welcome to use the quotient rule, but I just think that you would probably have a little more difficulty getting your answer kind of sufficiently simplified. Yeah. Okay, next up we have, what is it? H of x is equal to e to the x squared divided by x squared. So this is one where we do have to use the quotient rule. There's no way to simplify this, and so we're kind of forced into using the quotient rule. So how does the quotient rule work? Well, we start by taking the derivative of the top. So I'm going to kind of write this out in that placeholder notation because it's a little bit of a trickier one. So we have the derivative of e to the x squared, and then we're going to multiply that by the denominator. Then we're going to take the derivative of the denominator and multiply that with the numerator. And then we're going to divide that by the denominator squared. Okay, so what is the derivative of e to the x squared? Well, e to the x squared is a composite function, right? So the outer function would be e to the u, the inner function would be x squared. And so anytime you have e to a power, the first part of the derivative is just going to be exactly the same as the original function. So it's just e to the x squared. But then we need to multiply that by 2x because that's the derivative of x squared. And then we multiply that by x squared. Then we take the derivative of x squared, which is 2x, and multiply that with e to the x squared. And then in the denominator, we have x to the 4th. So let's simplify this a little bit. We'll see that because everything has some common factors of x, we'll be able to simplify. But let's start by rewriting this as, so it's 2x cubed times e to the x squared minus 2x e to the x squared, all divided by x to the fourth. So all of these have a factor of x. So we can get rid of this x, we can bring this down to being a 3, and then we can get rid of one of these x's and bring it down to being a 2. So our final answer will be 2x squared e to the x squared minus 2e to the x squared, all divided by x cubed. All right, there's one more from this question, so one more derivative, and then after this we'll get into some related rates problems. So this one is y is equal to x squared plus e squared, all divided by the square root of x. So this one is another good candidate for simplifying before taking the derivative. So what makes me say that? Well, basically, let me show you a situation where you could not do that. So let's say our function instead was like this, square root of x over x squared plus e squared. This one you can't split it up, right? Because you can't split a denominator up, but you can split a numerator up, right? Because if you're adding, so if you have like a over b plus a, or let me say it this way, a over c plus b over c, that's the same as a plus b over c. And so similarly, if you have something that looks like this, you can split it up. So in this case, we can take this, this function and rewrite it as x squared over square root of x plus e squared over square root of x. So let me write down, we're just simplifying. So why would we do that? Well, basically, at least for me, I like to avoid using the quotient rule whenever possible, not because it's like impossible to do it, but because it kind of makes simplifying things a little bit more annoying. In this case, it probably wouldn't be that bad, especially because when you do the quotient rule, you square the denominator, so that would just become x. But generally speaking, it's typically a little easier to simplify before, so that you avoid using the quotient rule. So what does this one here simplify to? Well, this is the same as x squared over x to the 1/2, and I'm going to rewrite this also as x to the 1/2. So x squared over x to the 1/2, if we subtract the exponents, we get x to the 3/2. Because 2 is 4/2 minus 1/2, we get 3/2. And then here, remember that e squared is just a number, right? If there's no x anywhere, no variable anywhere, then it's just a number. So we can rewrite this as e squared times x to the negative 1/2 and treat it just the same as you would if it were like 5 times x to the negative 1/2. So what do we get when we take the derivative? Well, the first part, we bring down the 3/2 and we get 3/2 x to the subtract 1 from 3/2, and that gives you 1/2. And then the second part, we just leave that e squared along for the ride because it's just a constant. We multiply it by negative 1/2, and then the new exponent is negative 3/2, subtracting 1 from negative 1/2. And so altogether, this simplifies to 3/2 x to the 1/2. And you could rewrite that as like a square root if you wanted to. And then this one would be negative, maybe I'll do it like this, minus e squared over 2 x to the negative 3/2. And of course, you could rewrite that. You could put that in the denominator. You could kind of change the way these fractions are written, but this would also be totally fine as an answer. Okay, so that was it for derivatives. The last thing we're going to go over in this video is some related rates problems. So that is number 7 and number 8. Okay, so number 7, and maybe actually, let me see how we are for space, because I might just do these. No, I'll do it over here. But actually, sorry, I'll go back here for a second so we can read it. So it says, a paper cup has the shape of an inverted cone with a height of 12 centimeters and a radius of 4 centimeters. If water is being poured into the cup at a rate of 2 cubic centimeters per second, How quickly is the water level rising when the water is 5 centimeters deep? And let me actually, sorry, I didn't do this ahead of time, but I'm just going to copy and paste that whole question so that we can just refer to it rather than have me rewrite it. Okay, so the first thing that we want to do, and I'll make this a tiny bit bigger. So the first thing we want to do is draw a picture of our situation. So we have a paper cup, and it's the shape of an inverted cone. That basically just means it looks like an ice cream cone. So we have a cup that looks like this. And it tells us that the height of the cup is 12 centimeters and the radius of the cup is 4 centimeters. So this measurement this way is 4 and this measurement is 12. Okay, so that's our picture. And then actually there's something else we should add here, which is that water's being poured into the cup. So that means that, maybe we should represent the fact that there's some water in this cup. So there we go. Okay, so next step that is a good one to take for related rates problems is basically choosing variables for the quantities that are changing. So we want to think about what's going on in this problem and what is it that is changing. So first thing to point out is that the size of the cup is not changing, right? It's not like a problem about a cup that's growing. What's changing is the amount of water in here. And so specifically, we could say, so it says water's being poured into the cup. So that means that the volume is changing of the water. So volume just means kind of like the total amount. The height of the water is also changing. And the radius of the water is also changing. Okay, so next thing we want to do is write down what is the given information and what are we looking for in terms of derivatives. And this step I just think is so important. I really think a lot of people, when you get stuck on these, it's because you skip that step. So this tells us that water is being poured into the cup at a rate of 2 cubic centimeters per second. So when you see this word cubic, that should help you kind of figure out what they're talking about here. So cubic means three-dimensional, right? So what kind of a measurement would be three-dimensional here? Well, volume, right? So dV dt is equal to 2. So what else is going on here? Well, the question asks us, how quickly is the water level rising? And so that means that we're trying to find dH dt. And then another thing, I know I've mentioned this a lot, but just to say it again, when you see this word when, that means don't write that information down. That's going to confuse you if you write it down at the beginning. Wait until the very, very end whenever you see that word when. So we want to kind of just work with this information to start with. And then we haven't made use of this 12 and this 4. We'll see where that comes into play in a moment. So if I gave you this question on the test, I would tell you the equation for the volume of a cone. I wouldn't expect you to know that formula. So that's what we want here, right? If we're trying to relate the volume, the height, and the radius, the equation that does that is that the volume of a cone is equal to 1/3 times pi times the radius squared times the height. So basically you're just looking at, anytime you're doing a related rates problem, look at these pieces of information and figure out what's the equation that relates them. And again, like I would expect you on the test to know things like the area of a rectangle or the area of a circle or the Pythagorean theorem or things like that. But as soon as it gets into like a more complicated equation, I would give it to you. Okay, so there's one issue here, which is that if we go and take the derivative of this, we're going to end up with dV dt, right, from this part. And that's okay because we have dV dt here. We're also going to end up with dH dt, and that's fine because that's what we're looking for. But then we're going to end up with dr dt, and we don't have any information about dr dt. We're not trying to find dr dt, and so that tells us that we're going to have too many unknowns and we're not going to be able to solve this. And so that's where this stuff comes into play, because we can use that information to get rid of r. So we did a question like this, or similar to this on a worksheet. And basically the idea is that if you think about it, any cone of water that you draw in here, so like imagine that this water level went down and now it's like down here, or when there was more water, you know, it looked like this. All of those cones have the same shape as the original cone, right? They're kind of proportional, you know, they're not, it's not like you would have a cone of water that was like super wide, like that, right? It has to fit into this cone. And so it kind of maintains those same proportions. And so what we can see by looking at the cup is that the radius is 1/3 of the height. And that's going to be the same thing that is going to happen for any of these sort of subcones that happen with the water. So looking at these things, we can say that the radius is equal to the height divided by 3. And so we can put that into our equation before taking the derivative. And we'll write that as now h over 3 times h. And then we can simplify this equation. And so let's see, so we'll get, let's put all the constants out over to the side. So we'll get pi over 9 times, oh, sorry, I left something out. This is supposed to be squared. My bad. So this should actually be pi over 27 because we have 3 and then we have 3 squared, which is 9. And then we are multiplying that with h cubed because we have an h squared and then we have another h. So now when we take the derivative, now we won't have any extra variables floating around that we don't have enough information about. So if we take the derivative of this, we get dv dt is equal to pi over 27 times 3h squared times dh dt. And we can simplify this a little bit because of the numbers involved here. So this becomes, so 3 and 27 can be simplified. So we get pi over 9 times h squared times dh dt. Okay, so once you're totally done taking the derivative, that's where you can start thinking about plugging stuff in. So we know what dv dt is, we are looking for dh dt, and so that means that the one thing that's remaining here to plug in is this h, right? We need to know what h is. And so if we go back to the question, that's where we see when the water is 5 centimeters deep. And so that means that we're plugging in 5 for h. So h is equal to 5. So we knew that dv dt was equal to 2, and so we get 2 is equal to pi over 9 times 5 squared times dh dt, and dh dt is what we're trying to find. And so we get 2 is equal to 25 pi over 9 times dh dt. And so we can multiply both sides by the reciprocal of 25 pi over 9. So if we multiply both sides by the reciprocal, we're left with this. So that means that dh dt is equal to 18 over 25 pi. And then let me see, maybe I have a decimal approximation for this. Yeah, so that is approximately equal to 0.229. And then what are the units? Well, if we look back at the original units in the question, the units for the change of volume were cubic centimeters per second, but here we're talking about a level like a change in height. And so that should just be centimeters. So this is going to be centimeters per second. All right, so basically just, following those steps that I outlined, I think is really, really important. And, that one, I think this question was specifically kind of a tricky question because of the, because of this business, or sorry, not that, because of this. But that really just is kind of looking at like, what is the information that's given? What are you trying to solve for? And do you really have enough information to solve or no? Alrighty, so next one is another related rates problem. So this one says, and I think I'm actually just going to copy and paste that again so that we can refer to it without having to go back and forth. So now we're looking at number 8. So this says, at noon, a cyclist starts riding north at a rate of 12 miles per hour. At the same time, a person starts walking from the same point, heading east at a rate of 5 miles per hour. How fast is the distance between the cyclist and the walker changing at 2 p.m.? So basically, we want to start by drawing a picture, right? So what does this picture look like? So they start from the same point. So maybe let's say that point is right here. And then we have a bicyclist. So here we have our bike. And then we also have a person walking, and that person is walking east, and they're going more slowly, so I'll make this a little bit smaller. And yeah, so that's where, you know, at some point in time, they're both a certain distance from their starting point. And then we're going to be interested in the rate of change of the distance between them, and so we want to complete this by making it a right triangle. Okay, so next thing is to figure out, you know, what is changing in this question and give variables to those things that are changing. So looking at our picture here, the distance between the starting point and the cyclist is changing, right? So we could call that distance maybe y. And then the distance between the starting point and the person walking is also changing. And then the diagonal distance between them is also changing, so that's z. So notice that this is different from that problem that was on your most recent test where there was a ladder. In that case, the hypotenuse was not changing, but in this case it is. So you really have to pay attention to the specific question and like just read it and kind of think about, is this changing, is this not changing? And use that to inform what gets assigned a variable and what does not. Okay, so next thing we want to do is, and maybe I'll write these down. So y is equal to the distance from the starting point to the cyclist. X is equal to the same thing, distance from starting point to the walker. And Z is the distance between. And you know, in this case, maybe it's not totally necessary to write this all out, but I think it's a really good practice in general to just like really be able to say it in words, because I think a lot of confusion arises sometimes when you're just kind of writing stuff down, but you're not like, in your heart, you don't really know what it means. So in this case, so now the next thing we want to do is look at what are the rates of change in this question, basically. So if we look into the question, we see that the cyclist is riding north at 12 miles per hour, and so that means that dy dt is equal to 12. We see that the person is walking at 5 miles per hour, so that means that dx dt is equal to 5. And then the question is asking us, how fast is the distance between them changing? And so that means that we're trying to find dz dt. Okay, so next up, we're going to write an equation relating the quantities in the question. So we have x, y, and z, and so that means we can use the Pythagorean theorem. So x squared plus y squared is equal to z squared. And then we can take the derivative. So we get 2x dx dt plus 2y dy dt is equal to 2z dz dt. So now we can start plugging some stuff in. So we know what dx dt, dy dt are. We're trying to find dz dt. Now we need to plug in some stuff for x, y, and z. So the question says, how fast is the distance changing at 2 p.m.? So that's a little different than some of the other problems we've done. We have to figure out what that tells us about x, y, and z. So how can we do that? Well, we know that they're traveling at, we know the speeds that they're traveling. And so we know that they've been traveling for 2 hours. And so we can use that to figure out the total distance. So basically, because they've been traveling for 2 hours, that tells us that, so x is the distance that the walker has traveled, right? And they're traveling at 5 miles per hour, so they have traveled 10 miles. And then y is the distance that the cyclist has traveled, and they're traveling at 12 miles per hour. So if we multiply that by 2, that tells us that they have traveled 24 miles. And then the distance between them, well, that we have to use the Pythagorean theorem. And so if you use the Pythagorean theorem, you should find that z is 26. So I'll just write that down. That's the Pythagorean theorem, or just the fact that it's a Pythagorean triple. It's a triangle with these kind of nice side lengths. All right, so now we can plug all this stuff in. So we have 2 times 10 times dx dt was equal to 5. And then we get 2 times y is 24, and dy dt was equal to 12. And then we get 2 times 26, and then dz dt is what we're looking for. And so if you go through all this arithmetic, which I don't think is really worth your time to watch me do, you end up with that the rate of change is equal to, 13. And the units are miles per hour, as we saw in some of the earlier units used in this question. All right, so that is it. And in the next video, I'll go over some questions from the second part of the review. And yeah, I'll see you then.